Welcome to the second part of Lecture 5. In the first part of this lecture, we examined Buckingham's pi theorem. We found the number of independent dimensionless groups used to define a problem. And we did a small example of how to design an experiment and process the data that we got from that experiment. In this part of Lecture 5 and in the next part of Lecture 5, we're going to do two more worked examples on how to use dimensional analysis in a chemical engineering context. In this part of Lecture 5, we're going to look at how to design a small-scale model of a large piece of equipment. Now, the key thing to remember when we do this is always keep your practical engineering head on your shoulders, because whenever we're building a scale model, we need it to be safe, we need it to be physically realizable, and we need it to actually work in the same physical and geometric manner as the large-scale object that we're trying to understand. So the context of the example we're going to look at is a big fluidised bed. Remember that the ghosts of engineering past told us all about fluidised catalytic crackers on refineries. And these were huge things, many metres in diameter and many tens of metres tall. Before you go and build something like that on plant, you want to make very sure that you understand how it works. And so you'd build successive scale models of it. So here on the whiteboard is a problem statement. We need to make a scale model of a fluidised bed cat cracker. The one on the plant is 2 metres in diameter, so it's quite a small one, operating at 480 degrees C with 1.5 millimetre diameter catalyst particles. We've got values there of gas viscosity and density. It's a hydrocarbon gas, 0.043 millipascal second viscosity, 0.45 kilos per cubic metre density, and the catalyst density is 2600 kilos per cubic metre. From operating experience, it's known that the superficial fluidisation velocity is 1 metre per second. Now let me explain that term. The superficial fluidisation velocity in a fluidised bed is the minimum velocity of the gas required just to float the particles on a bed of gas, so they're not a solid anymore. So, what we want to do is to try and find two things. We want to find the key independent non-dimensional groups that govern this problem. What we then want to do is to work out what the scale model looks like. The scale model we want to build in the lab under nice safe conditions, so it's going to be operating with cold air. We've got a density and viscosity value there for air at 25 degrees. We need to find what particles we're going to use, their diameter and their density, and we need to find how big, what our reactor diameter is, in order that we maintain geometric and dynamic similarity for our small scale model to our plant item. So that's the problem. First step, as ever, draw a diagram. So there on the whiteboard, I've put a diagram of the fluidised bed reactor, and I've labelled it with the parameters that I think are important. The minimum fluidisation velocity, U, is marked there in red. That's one of the things I need to find. And the other parameters of the problem I've also marked. So the parameters in blue relate to particles, so particle diameter and particle density. The parameters in purple relate to the gas viscosity and density. G is my acceleration due to gravity, and capital D is my reactor diameter. Okay, let's next find out which groups are present. Let's invoke Buckingham's pi theorem. We know that there are 7 parameters. Those 7 parameters are governed by the same 3 fundamental dimensions: mass, length, and time. So we're seeking 4 groups. Let's find those groups. Now the first group's really easy to find, because if we look at our diagram, we can see we have a ratio of 2 length scales, d upon d. So that is going to be pi 1. Let's have another look to see if there are any material property ratios, and look, we have 2 different densities. We have a gas density and a particle density. So let's make a ratio of those and call that pi 2. 2 groups, very easy to find, less than 30 seconds. Now, let's think about the physics of the problem. We have a fluid flow. We have a gas flowing through a packed bed, which will become a fluidised bed. There is going to be an interplay between viscous stress and inertial stress. So we expect the Reynolds number to be important. Is the flow turbulent or is the flow laminar? If we look at the parameters that we've chosen to describe the problem with, we can see that we can indeed form a Reynolds number with respect to the reactor diameter or with respect to the particle diameter. And it's up to you which diameter you choose. I've elected here to form a Reynolds number with respect to the particle diameter. So I'm interested in the fluid flow around a particle rather than through the reactor body. Because in reality, the fluid doesn't flow through an empty reactor of diameter d, it flows through around billions of little particles of diameter little d. And so that length scale little d is going to govern the nature of the flow around each particle. And also, all the heat and mass transfer for this problem takes place around the surface of the catalyst. And so again, that becomes an important length scale to look at. We need one more dimensionless group. Imagine, if you will, that our particles are fluidised, they're on that bed of gas, and we remove the gas. They all fall back down to a rest position. And so there's an interchange of potential and kinetic energy, depending on how we use a length scale to describe that. So let's seek a Froude number. Froude number we write as a velocity divided by the square root of the product of g and d. We have all those parameters, so we can say dimensionless group number 4 is our Froude number. So there are the 4 dimensionless groups that describe this problem. Now, what we're going to do is we're going to calculate values of each of those 4 dimensionless groups for our plant item, and we need to ensure that our scale model also captures the same values of those dimensionless groups. Then we've achieved geometric and dynamic similarity. All the ratios of length scales are the same, and all the physical processes are the same. So let's go through now and start looking at my dimensionless groups. Let's start with pi2, which was my density ratio, my density of my gas divided by my density of my catalyst. I have enough data from the plant to work out what pi2 is on the plant. It's 1.7 times 10 to the minus 4. So that needs to be preserved in my scale model. I know that in my scale model I'm using air, so I know my air density, which allows me to work out what my particle density should be, 6930 kilos per cubic metre. So, take a step back and think, can we select a material with a density that high? So you might look through a table of physical properties and find that antimony is quite close, 6,700 kilos per cubic metre. I would hope you would also look through the material safety data sheet, which is a document that describes the chemical and physical properties of that material and gives you all the safety and hazard information for that material. If you read the hazard section of the material safety data sheet for antimony, you find out that it's actually very toxic. And so we reject the choice of antimony based on safety grounds. So let's find another material with a high density, cerium, 6,770 kilos per cubic metre. Again, referring to our material safety data sheet and looking at the material hazards, we find that it's toxic, so we reject cerium on the grounds of toxicity. We find our table of material properties again and find iron. Iron has a density of 7,000 kilos per cubic metre, actually closer to that we desire. We look through the material safety data sheet and find that it's pretty safe. And so by choosing iron here, we have selected an inherently safe material. There is no hazard associated with it, so therefore we don't have any hazards that we need to control. Inherent safety is very important. So we've got a nice safe material, it's cheap, it's readily available. Let's have a look at the next dimensionless group. So for our plant, we can have a look at the fluid flow, and we have a look at the Reynolds number, and we've got enough information to calculate that the Reynolds number with respect to particle diameter is just below 16. That should trigger the thought that this is a laminar flow, and so we need to preserve that laminar flow characteristic in our scale model. So for our scale model, we can use pi3's value, 15.7, to work out what D and U should be, but we don't have quite enough information to work out what D and U should be individually. We can, however, work out their product. So the product du is 2.35 times 10 to the minus 4, and we need more information to individually calculate both D and U. So let's see how we can get more information. Let's look at another dimensionless group. Let's look at the Froude number. The Froude number usefully also has U and D associated with it. This is good. And we can work out that pi 4 is going to be roughly 8.2. Fine. And therefore, we can use that information along with the information about the product of du from Reynolds number to work out that our particle diameter in our model has to be about 440 microns, and our superficial fluidizing velocity on our model is just over half a meter per second. Again, stop, take a step back and think. 440 micron particles. Can we achieve this? Yes, we can. Is it safe? 440 micron particles with high density aren't going to remain suspended in the air. They're not a dust hazard. They're not nanoparticles. They don't have the ability to pass between the blood-brain barrier. So there's unlikely to be any safety concerns associated with using 440 micron iron particles. Let's think about the fluidizing velocity, 0.5 meters per second. Is that safe? Is it achievable? If this was 50 or 100 meters per second and things went wrong and that gas blew out all our iron particles at 100 meters a second, that could cause quite substantial damage both to a person and to equipment. And so we would reject a velocity that high. Half a meter per second is not going to cause too much damage. There's not a lot of kinetic energy associated with the particles at that speed. So we're happy with that and we can easily achieve it. So both of these values are safe and practically achievable. So this is looking good. We have one more dimensionless group to find. Now that we know our particle diameter, we can work out our model reactor diameter, big D. From our plant data, we see that dimensionless group pi1 has a value of 1,330, which we need to preserve for geometric similarity. And our scale model, therefore, should have a diameter of 0.59 meters. Again, stop and think. Is 0.59 meters safe? It's going to be about that big. We're probably going to make it out of plastic. It's probably going to be about that high, roughly. If that falls over, is it going to cause much damage? Not really. If it was 2 meters in diameter and 5 meters high and fell over, it could crush someone or something. And we would reject something that large and rework our problem to find something smaller. But a diameter of 59 centimeters, we're happy with. So, let's run through and have a look at our dimensionless groups, and we're going to compare full size to model. And in each case, we can see that the full size dimensionless group and the model dimensionless group is the same. So that reassures us that we have achieved dynamic and geometric similarity. And so we can go ahead and build our scale model. Let's recap a few key points. What I wanted to demonstrate was that dynamic and geometric similarity are very useful tools for building scale models of real systems, and chemical engineers have been using these concepts for over 100 years. Buckingham's pi theorem gives us the number of independent non-dimensional groups that we need to seek in order to define a problem. Now, big key point. Always critically assess the values that you've calculated for your parameters for your model. Are they safe? Are they physically achievable? Are they practical? Is it cost effective? If you can answer yes to all 4 of those questions in that order, then you can go ahead and build it.